Right. So I want us to focus on the discrete distributions or probability distributions. Under the discrete probability distributions, we have the binomial distribution, geometric distribution, negative binomial distribution, hypergeometric distribution, and Poisson. But in the interest of this study, we will focus on binomial, Poisson, and the geometric distribution, because that's what you did. So let's just focus on this and leave these others in the meantime. So what do we mean when we say we're talking about the discrete probability distributions? Um, we zero in by looking at what is known as a random variable. When you look at the random variable, let me just define a random variable for you quickly. So a random variable can be defined to us as a numerical description of the outcome of an experiment. So the numerical description of the outcome of an experiment is what we call a random variable. Thus, the random variables associated with numerical values with each possible experimental outcome. So you find that the random variables can either be discrete or continuous random variables. Okay, so what do we mean when we say the random variables are discrete? I've already defined the random variables, that is just the numerical description of the outcome of an experiment. Whenever you're conducting an experiment, it could maybe throwing a coin or tossing a die or doing whatever you're trying to do, whatever the experiment that you're trying to do. Then the numerical description of the outcome of that experiment is called the random variable. Okay, so the random variables, we have said they can either be discrete or continuous. So what we mean when we say the random variables are discrete, we are talking about the random variables can assume, we are trying to say to mean that we have the counted number, okay, of values that are being assumed by these random variables. That's by discrete. So for example, we are trying to say we're looking at the finite cases. So for example, that include the terminating values. So for example, you can say the number of the students, let's say, that are trying to do the course. What course is this? Let's say this same business math and statistics, and the number of days in a week, okay, the number of visitors that try to visit your home, those can still be called the discrete random variables because they give us the number that terminates, okay? Yeah, how many people are there? They don't, they basically terminate, you have those numbers, those figures that you can easily count, 1, 2, 3, 4, and 5. But when you talk about the random variables that continuous, when you say the random variables are continuous, we mean that they assume a numerical value in an interval or a collection of intervals. Okay, for example, the weight. We can say, oh, this one is 65.5 kg. This one is 71.345 kg. Amount of rainfall, we can say this is 37.55 millimeters. Okay, the distance covered, it can be maybe 5 kilometers and 5 meters, 25 seconds, those things. Yeah, so in short, when you're talking about continuous random variables, these numerical description of these experiments, they do not assume a terminating figure. Instead, they give us the numerical value in an interval or a collection of intervals. That's what random variables are. So as for today, we want to look at the probability distributions that focus on the random variables that are discrete. And I've already said what discrete random variables are. So to be specific, for the sake of the exams and what we saw in the assignments that you had, you need binomial distribution as one of the measure. So now observe what is going on. What is binomial distribution, or when do you use this one? Okay, this one is basically associated with a multiple step experiment. The following are the properties, and you pay attention to the properties of a binomial experiment. Okay, when do we use binomial? The exam, in an exam or in a test, they will not specify that use binomial. Okay, use this, but you should be able to make assessments. So the following are the characteristics or the properties of binomial. Number one, the experiment consists of a sequence of any identical trials. That is to say, you can be trying and doing this experiment again and again. So you have a specific number of times that you have to try to do that experiment. Take, for example, you are tossing a coin and you want to get a head. So maybe you can say you are tossing it 10 times and observe how many heads you're going to get, or how many times you're going to get a head. So that's what it means. So in short, you have a limited number of times that you can try and try. Okay. The two outcomes are possible. Always when you're reading the question, check, do we have like only two outcomes possible? We only have two outcomes possible under binomial distribution, and these are referred to as a success and a failure. So what is a success? A success simply means when you get what you are looking for. For example, you're tossing a coin with a view to get a head, okay? You're tossing a coin with a view to obtain a head. So you start tossing your coin maybe 20 times. Whenever you get a head, maybe on the trial number 5, that is your success. Whenever you get a head, that's your success. If you get the otherwise, that's your failure. Okay, so we just always have only two options or outcomes. Sorry, we just have only two outcomes under binomial distribution. So just for example, a good example is of a coin. Whenever you toss a coin, you only have only two outcomes. You can either have a head or a tail. Okay, then the probability of success is denoted by P, and it does not change from trial to trial. So, and the probability of failure remains 1 minus P. From the concept of complement probability, we know that when we add the probability of success plus the probability of failure, they should give us 1. They should always equal to 1. If we say that the probability of success is represented by P, then P plus the failure, let's say our failure shall be Q is equal to 1. So whenever you want to make the probability of success, P, the subject of the formula, what am I trying to say? Sorry. I'm trying to say that whenever you add the probability of success plus the probability of failure, they should equal 1. Okay, they should always equal 1. Yeah. So if the probability of success is P, then the probability of failure is always what? 1 minus P. We want the probability of failure. We are given the probability of success as P, right? So since we want failure, we make failure the subject of the formula. So the probability of failure shall be given as 1 minus what? Minus the probability of success, P. So that's how we get this 1 minus P. And it does not change. It remains the same. This is under binomial. You just pay attention to these characteristics first before you can do questions. We're going to do questions. Don't worry about questions in the meantime. So when you observe that the probability of success remains the same throughout, it does not change. For example, when you throw a coin up, you always expect a head and a tail, and the probability of getting a head is always 1/2, right? It's always 1/2. we know that the probability of getting a head or a tail, let's say a head, from one coin, a coin, the ordinary coin that we're talking about that ordinary. The way how it was, the olden days, a coin had the one side, it had a head, then on the other side, it had a tail. I'm trying to make you understand. So what will also happen is that when you throw a coin up, it can either land on this side, which has a head, or on the side that has got a tail. So how do you come up with the probability maybe of getting a head? The probability shall always be calculated as favorable outcome, what you're looking for, all over all possible outcome. This is your probability. All possibility, all possible outcome, or total possible outcome, right? So what is the probability of the favorable one? The favorable outcome is what we are looking for. If we are looking for the head from the tail, we count how many heads did we have in this experiment. We only have only one head. Okay, from one coin, we just have only one head. And how many possible outcomes? They're just two. It can either give us a head or a tail. Therefore, that's how we get 1/2. Now, this probability remains the same. The probability of getting a head will always, from one coin, it will always remain 1/2. Even if you throw the coin 100 times, it will just remain 1/2, 1/2, 1/2, because you are throwing the same coin. It has not changed. It applies the same to the tail. Still, the tail we just have only one tail and two head and two sides. And so even for the tail, it's still 1/2. It remains the same. So now, if we know the probability of success as 1/2, which is same as 0.5, so this is our P, right? It means that the probability of failure shall be 1 minus P, which is 1 minus 0.5 in the context of the coin. If you are throwing a coin, one coin, again and again, many times. So we know that the probability of failure 1 minus P shall be given as 0.5. In this respect, we find that the probability of failure 0.5 and the probability of success 0.5 is just the one and the same. But in most times, you find they are different. It's just under this context of when we're using the coin as an example. Yeah, so that's what we mean when we say that the probability of failure does not change and the probability of success from trial to trial. So whenever you throw one coin, even if you throw it 100 times or 1,000 times, it will still just give you two sides, a head or a tail, just like that. So that is one of the properties. Then the other one is these trials are independent. It's another property, the fourth one. The trials are independent. And what do we mean when we say that the trials are independent? We're trying to say that the previous trial does not affect the next trial or the current trial. So if last time when you threw this coin up, you had a head, it doesn't mean that since you had a head last time, next time you should get a tail. You can, no. Why can we just keep on getting heads and heads? It is possible you throw it the first time you get a head, the second head, third head, fourth head, fifth head. And it won't be like, no, now why are we getting only heads? Therefore, the sixth one, we are tired of getting head, should be what? Should be a tail. You basically have no control over this. When you throw a coin, you don't control how it is going to land. It will just fall and land from either of the sides. So this is what we are trying to say when you say that the trials are basically independent. So you should be able to see these characteristics or these properties in the question, every question that deals with binomial probability distribution. Observe this and see these characteristics, see these properties, examine. Once you find them that they are there, then you can proceed now and apply the formula, solve your question. So the questions that you ask yourself whenever you find a question, number one is, how many trials are there? Do we have specific number of trials in these experiments? That's question number one. You are given n, the value of n, the specific number of trials that are there. Number two, how many outcomes do we have? Do we have more than 2 outcomes? If there are more than 2, then that is not binomial. Binomial is only 2. Then you go to number 3. How is the probability of success and failure? Does it remain the same throughout? It does remain the same. Then are the trials independent? If they are independent, then you're using what? Binomial distribution. Therefore, a random variable will follow binomial distribution, and this will be denoted by this one. Okay, this will be our formula. It's a formula that we're going to be using. Okay, where we say the probability, this P is probability of X, the random variable, this small x, is equal to probability of success. I said P is the probability of success multiplied by X, and multiply all that by 1 minus P, which is the probability of failure. Then you say 1 minus what? Minus X. 1 minus X is 1 minus X. 1 minus X. Then this same one now, we can rewrite this as say, we can give the formal definition to the same, and the formal definition shall be n minus c. Instead of where we had put 1, we can say n minus x. Yeah, n minus x. Okay, so that is to say, okay, let me just highlight this a bit before we can proceed so that the air is cleared. When you just have only one trial, okay, when you just have only one trial, we know that the combination of 1 and 1 is 1. So we have this. But when you have more times now, when you're trying more than 1 times, what you will have is to do these combinations. You do the combination so that your formula can be the probability of the random variable x that follows the binomial distribution should be given as the combination of n and x multiplied by the probability of success x to the power x, multiply that by 1 minus p, which is the probability of failure, to the power n minus x. Yes. So now we need to give the definitions to these numbers. Okay, we need to give the definitions to these, or they need to be defined to us so that we understand what is n, what is x, what is 1 minus p. We are saying that p is the probability of success on a simple and single trial. On a single and simple trial, the probability of success shall be represented by p. We know that in each experiment, we are just repeating the experiment several times. So now you just check on one trial, what is the probability of success of getting what you want? Okay, so that one will be given as a p, will be denoted by p, and the 1 minus p is the probability of failure on a single trial. Any, what is our n? Our n is the number of independent trials, the number of times that you're going to try or you're going to do that experiment, so that this x, the small x, this small x, is given as the number of successes in any trials, okay? Or in the total number of the trials. How many times are you going to try it? Take, for example, you're throwing a coin 20 times, okay? Your n shall be 20. Then the question is, how many times, what is the probability that you're going to get maybe 80 heads? So 80 heads, 8 shall be your x. whenever you get a head, if you're looking for heads, it's a success. So what is the probability that you get eight successes, meaning 80 heads? So that is your small x, and that is how these letters are defined here. Okay, you can use some literature use other, some books use other letters, but most of the literature they use these ones. Yeah, but sometimes you may find that they define the x as k somewhere, but the definition is still the same. Like they can use k instead of x. The definition is still the same. That's how they are defined. That's what they are. So now, still on the formula, this nx, this one is the combination, okay? Is the combination. And how do you do the combination? I think the easiest way is to use your calculator. I think this one is the easiest. In statistics, they allow you to use calculators. You can relate this as n, the combination of what? Of x. Okay, n combination of x. N combination of x, how do you do it on your calculator? Take, for example, on n here, you have a number 6 and 2, like this. 6, the combinations of 2. That simply means that you can just press 6. You press 6 on your calculator, press 6, then you do combinations of 2. Where do you get now combinations of 2? On your calculator. The feather should be the feather upper left. There's a part which is there's a button on your calculator that is written as CR. Should be there. Anyone just to confirm who is learning with the calculator? There's this button. Should be this button on the upper, should be upper left. What calculator is that? Should be Casio or some other calculators.
Yes, it's there. It's there.
It's there, eh? Yeah, that
yes,
part,
sir.
once you just press the number, maybe 6, then you press this button, it will write C2 like that. And can you just confirm for us, what is this, the 6 combinations of 2? Like you press 6, combination of 2. Like 6, then you press that button, then you write 2. What does it give us?
It's 15.
It gives us what? 15.
15.
That's right. Confirmed.
Yeah, it's right. Huh? So that's how you press this one. That's how you work out this part. This part is always a combination. Then P is the probability of success that I've already defined. 1 minus P is the probability of failure that I've defined. And N is the number of trials, independent trials that you're going to make. And X is the number of successes in any identical trials that you're going to be doing. All right. Now that we have gotten this one and we are fine with this one, we need to do a question. I think the question will make sure that we are fine. Once we get the question, it should be fine. Here's an example now. Let's have an example here. An example is, let's assume that a fair coin is tossed how many times? 3 times. Okay, it's a coin, it's a fair coin. One coin is tossed 3 times, meaning you throw it 1, 2, and 3 times. That's the number of trials. In other words, you have tried this experiment. Tossing a coin is an experiment, but how many times have you tossed the coin? You've tossed it 3 times. So the number of trials are 3 times. What is the probability of getting 2 heads? Whenever you get 1 head, that's your success, okay? Then you are asked to find the 2 successes, meaning we know that our successes are represented by the small x, meaning your small x shall be 2. I said that the number of successes is denoted by the small x. And what is success? Simply means that whenever you get what you're looking for, in this respect, we are looking for the heads. What is the probability of getting 2 heads? Once you get only 1 head in one trial, that's your success. So the question is that if you throw the coin 3 times upward, how many times, what is the probability that you have 2 heads? Meaning at one time it will give you a head, maybe the other time a tail, then the third time will give you maybe a head, or maybe a head, then a head again, then a tail. So what is the probability that whenever you throw it, you at least you have 2 what? 2 heads. At least you have what? 2 heads, or head, tail, then head. But at least you have 2 heads in each independent track. So the question is, what is that probability? That maybe the first time to give us a head, and the other one a tail, then the other one a head again. So what is the probability that we get 2 heads? That's my question. That's the question we are being asked here. So we need to define this according to the formula that we have. We're given that the probability that follows this binomial distribution is given as n the combinations of x, the probability of success x, multiply that by 1 minus p, and we raise this to n minus x as an exponent. We have defined our n. Our n is 3 because that's the number of times. Okay, that's the number of trials. Then our p is the probability of success in each independent trial. So the question is that when you throw 1 coin, what is the probability of success? That is your p. The probability of success is getting a head. So in short, what is the probability that you get a head when you throw the coin once? I've already said that you always find that as 1/2, right? Because there is only 1 head on each coin and 1 tail. So you have half as your p. Therefore, you can factor out all these other things and substitute into the formula. We have our n as 3, the number of times or the number of trials. The small x, which is the number of successes, are just 2 heads. And the p, the probability of success from 1 independent trial is 1/2. Therefore, the probability of failure 1 minus p should be 1 minus half, which is half again, right? Half this half, we can still write it in decimals as 0.5 or 0.5 is still the same thing. Then we can just substitute into this formula. We just substitute into the formula. Just do the computations, you substitute. Where there is n now, we put the value of n. We say the value of n is 3, right? The value of n is 3, the combinations of 2, like that. The probability of success is 0.5, which is as good as half. To the power x, our x is 2. We say that this is the number of successes. 1 minus p, 1 minus 0.5. To the power, our n, the number of trials are 3 minus 2, like that. So that we can have 3, the combinations of 2, and we have 0.5. We raise this to the second degree. 1 minus 0.5 is 0.5 to the power 1, like that. So now how do we solve this? You do 3 combinations of 2. 3 combination of 2. Anyone to give us the solution? 3 combinations of 2.
I don't know. It's giving me 3.
It's giving us 3.
Yes, it's 3.
Okay, it's 3. 3 times what is 0.5 raised to the second degree?
Zero 0.25.
0.25 times 0.5. Can we do just the multiplication of all these 3? 3 times 0.25 times 0.5. And what do we get as our x?
0.375.
0.375. 0.375 as the probability of getting what? 2 heads. So this is our probability. Our probability of getting 2 heads is 0.375. Are we fine? Do I have a question?
So I have a question.
Yes.
Where did we get 0.5 from?
Or 0.5 is the probability of success in the independent trial. Okay. So the probability of success is half for a coin, right? Once you toss a coin, the probability of getting a head is 1/2. Half. Then the probability of failure is 1 minus the probability of success, which means if the probability of success is 0.5, then the probability of failure will be 1 minus 0.5, which will still be 0.5. Are you fine now?
Okay.
Okay.
Yes, sir.
What is 3 divided by 8?
It's given as 0.375.
Okay, 0.375. So, which is just the same thing. So if you want, I was just trying to show you that you can still do it as fractions, okay? You do it as fractions. It's still the same answer, but I would recommend that you just convert the fractions into decimals. That's the easiest way of doing this. Still the same. You can still leave your probability as a fraction. Is still getting to give you the same answer. All right, we can do the second example. The probability on the binomial. We are still on binomial. The probability that a defective pen is drawn from a box of pen is 0.1. The same. The probability of getting a defective pen from a box is 0.1. Now, if you sample 6 pens, find the probability that that sample will contain the following. You will contain, number 1, non-defective pens. Okay. So you have in a box, like the probability, you are given that the probability of getting a defective pen in this scenario is given as 0.1. That's the probability of getting the defective pen. Now you are given, you sample at random, okay? You just sample 6 pens. Okay, so I was saying that you sample at random 6 pens, okay? Just get 6 pens at random. Then the question is, from those 6 that you have selected, given that the probability of getting a defective pen is fixed as 0.1, what is the probability that you have no pen that is defective? That's a question. You have non-defective pens. What is the probability? So we identify our figures. Number 1, the probability of success. So in this respect, since we are looking at, the question is focusing on defective pens. Whenever you get a defective pen, that's your success, right? So the probability of success for each independent trial is fixed at 0.1. That's your P. And then the probability of failure is 1 minus P, which will be 1 minus 0.1. And this should give us 0.9. Should give us 0.9. That's the probability of failure. 1 minus P is given as 0.9. Then we also have N, the number of trials. Okay, we are given that we have just sampled 6 trials, 6 pens. So from the 6 pens, or the number of trials is given as 6. Then what do we have? The number of successes, X. The number of successes. I said that your success is to get a defective pen. Since now question number 1 is asking that you have no defective pen, it means that your success is what? It's 0. You have 0 success. You have no pen, no defective pen, meaning you have 0 what? 0 success. Having gotten these, then you can just compute into your what? Your formula. And your formula is always n, the combinations of x, probability of success to the power x, multiplied by 1 minus p, which is the probability of failure, to the power n minus x. Get these numbers and just substitute into this formula, and then you get the solution. So there we go. Let's go now. What's our n? Our n is given as a, what is our n? Our n is 6. 6, the combinations of x, our x is 0. 6 combinations of 0. Our probability of success, p, is 0.1. 0.1 to the power x is 0. Multiply that by 1 minus p, which is 0.9, to the power n, 6 minus 0, which is 6. And you can do the computation of this one. What is 6 combination of 0?
It's 1.
It's 1. Whenever you combine the, yeah, whenever you do the combination of n, n number given the combination of 0, you get 1. Yeah. Then we know that once we multiply this 0.1 to the power 0, it will be 1, because n number raised to the power 0 is 1 as well. Then multiply that by 0.9 to the power 6. So in short, just give us what is 0.9 to the power 6. What do we get as the solution for getting 0 defective?
Zero 0.531441.
0.531441. Exactly.
Yes.
So this is the probability. You know that always the probability is between 0 and 1. You cannot have the probability at 1 point something or negative, like it's less than. No, like under these discrete probability distributions should get this. Your answer should be between 0 and 1, meaning you can get 0 point something. Yeah, so that's what is there. That's the probability that we're gonna have 0 success. Then any question from anyone?
Sir,
Madam.
I think I've missed out there where you wrote 1 minus p equals to 0.9. I don't know how you came up with that.
Oh, okay. We know that our P is our success, the probability of success in each independent trial. And we're given that in this context, our success is to get a defective pen. It is defined in the question that, here is your question. Your question defines, it says that the probability that a defective pen is drawn from a box is always 0.1. So your probability of success is 0.1. So to get the probability of failure, just say 1 minus 0.1, and you get 0.9. That's what you put under 1 minus p, which is always our probability of failure. You got it?
Yes, sir.
Okay, thank you. Right. Progress. We got to the second one. What is the probability that you have 5 or 6 defective? Listen now. Whenever you find the word or simply means add, or and the either. Okay, that's how you use these words. They mean add. But if you find the and the, okay, and the both these two, they mean multiply, like it's times. Pay attention to that. Okay, they mean times. Okay, now when you find the yeah, so our question is asking that what is the probability that you get 5 or 6 defective? So this one, our n still remains the same. It's still the sample of 6, and the probability of success remains fixed as 0.1. The probability of failure remains 1 minus p, which is 0.9. But what is now changing is x, the number of successes. So now, what is the probability that we get 5 or 6 successes? What it means is that you have 2 here. You have to do 1 for when x is what? Is 5, and when x is what? Is 6. You do these separately and then you add them. Okay, you add them. Once you add them, you get the solution. That sum is a solution that you're getting. So let me just show you what we're trying to say. You are repeating the whole process. That's what I'm trying to say. You're just repeating the whole process. Okay. You are saying 6, the combination of you have 6 combinations of, let's use 5 now. 5, probability of success is 0.1. And the number of successes now is what? Is 5 successes. Then the probability of failure is 1 minus p. Then to the power n, our n is 6. 6 minus 5. This is the first one. Then you should add 6 combinations of, you do this one now, when the number of successes is 6. So 6 combinations of 6 multiplied by 0.1, that's the probability of success, to the power 6 now, that's your x. And multiply that by 1 minus p. What is 1 minus p is 0.9. 1 minus p is 0.9. That's what I've said. Even here on top here is 0.9. We found it. To the power 6. Now we know that 6 minus 6 is 0. So that's how we put what? 0 here. You're just replacing into the formula. So once you do this one, the same way, 6 combinations of 5 times 0.1 to the power 5 times 0.9 to the power 1. You get that solution. Then you should add this one, 6 combinations of 6, 6 combinations of 6, and multiply by 0.1 to the power 6, multiply by 0.9 to the power 0. What is the 6 to the 6 combinations of 5? Let's do the top one. What is 6 combinations of 5?
6.
It is 6?
Yes.
Okay. 6 times, what is 0.1 to the power 5? 0.1 to the power 5. Hello? Anyone can confirm, please, so that we save our time. What is 0.1 to the power 5? Okay. All right. So, all right. So 0.1 to the power 5, you multiply that solution. Sorry?
0.59049.
0.594. Okay, multiply that now by 0.9. That answer times 0.9. This one. It's what?
Sorry, sir, you are blocked when you said what?
As I said 0.1 to the power 5. That answer now times 0.9. What do you get? Yeah, so it's important. Times 0.9. Okay, so it's important that whenever we come for the class in mathematics and statistics, we come with a calculator, wherever we should be following. That's when you can easily be connecting and getting these things. So I recommend that you just have to do as if you're coming for the class, get ready, and yeah. So once you do the multiplications, the solution that you find, you add, right? And you add, you do again for this one, downward, straight, the same procedure. Then you add the two answers. Once you add the two answers, you add the two answers that you're going to find are these, and then the solution you find is this one. So this is the probability that you get 5 or 6 heads, right? Then the third question is asking that what is the probability that you get at most? Now listen, the way how we use these words in statistics is different. You have to pay attention to the way how these words are used. When you use the word utmost, the word utmost simply means less or equal to, okay? It simply means less or equal to. Then if you use the word at least, the word at least simply means greater or equal to, all right? Greater or equal to, not more than. We know that not more than means less or equal to, okay? Yeah. Exceed, not exceed, you know, those words. So you just have to pay attention to the way how the words are used. So we are asking that now that the probability that at most, meaning less or equal to 1, is defective. What is the probability that less or equal to 1 is defective? So that is just given as the probability that x is equal to 0 defective plus the probability that the small x is equal to 1. Because we're including 1, we are saying less or equal to 1, which means what is less than 1 is 0 defective and 1 defective. Just add these two. What do we mean? We can do everything remains the same. Our number of the sample size remains 6. Our P remains the same, 0.1, the probability of success. 1 minus P still remains 0.9. And then our X now shall change. You have the one for 0 and then the one for 1. you add, repeating the same procedure just as it is depicted here. You repeat the same procedure, substituting into the formula. You get this as the what? As the solution. That's what you get, 0.88573735, sorry. That's what you get as a solution. Then what is the probability that at least, okay, at least one is defective? Now, at least one is defective simply means that greater or equal to 1. So greater or equal to 1 is defective. So which simply means that it can be from 1, 2, 3, 4, 5, and 6 what? Defective. That's greater or equal to 1. Which means what is excluded here is just 0. Okay, the probability that 0 is the defective. Therefore, the easiest way, we know that all the probabilities add up to 1, right? All the probabilities add up to 1. So you can say 1 minus the probability that the small x is equal to what? To 0. And it will give you the solution. So what is the probability that small x is equal to 0? We had already found it. Using the same method, everything will remain the same. N shall be 6. Our p remains 0.1. Our 1 minus p remains 0.9. And then your x, the probability of success now will be 0. When we find that solution, this one, you should subtract it from 1. So whatever you get, that is the probability that at least 1 will be defective, which is just given as 0.468559. It is basically the same way of doing the thing. So any question?
Hello.
Yes, sir.
Maybe just as a reminder that we are brushing up on our probability knowledge. Exceed and not exceed. Again, just maybe remind us on that.
Don't do that. You're going to destroy the calculator. You don't press like that.
Sorry?
Yeah, so on exceed and not exceed, when you find exceed and not exceed, or not exceed, it means what?
Oh, okay. When you say exceed,
Yes.
Exceed simply means greater than, right? That's exceed.
Okay. Okay.
Not exceed simply means less than. There's a sharp relationship. It's not a weaker one. Yeah.
Okay. All right.
Yes, sir. Thank you.
All right. Thank you.
So there is no inclusion. It is not included. Yeah, but
That's
if you
right.
say less or equal to, then there's an inclusion. This is a weaker relationship. Thank you.
Okay. Thank you.
You're welcome, sir. Right. And the time is 20:05. The time is 20:05.
We can continue, sir, since it's 20:05.
It's 21.
It's 21:05. I want to get the feel of the class. Can we continue? Maybe we can continue for 20 minutes, then we can be done. Are you fine with that?
I think it's fine with me.
It's fine. We can continue for the next 20 minutes, maybe.
Continue, sir.
Yeah,
Okay.
it's fine with me as well.
Okay, let's continue, Kansh. Let's continue. Those who are busy will record the class. The class is being recorded. They will find time to do the thing. Okay, now let's discuss Poisson distribution as projected. Poisson now. Okay, don't forget, but yeah, let's move from binomial now. What about Poisson? So what you should do, you just pay attention to the way how the random variable is defined, or the properties that underpin the distribution, probability distribution. So the Poisson distribution is a probability distribution that is useful in describing and estimating the number of events that will occur in a specified period of time or in a specific area. This is how it is defined. So it is used to describe or estimate the number of events that will occur in a specified period of time or in a specific area. Yeah. For example, examples where you use binomial Poisson distribution, pay attention. There is an element of time always. Always. You're given some time. There should be some time. So you should examine in your question, do we have the element of time? Time should be there. That's when you can use Poisson. Time should be there. So number one, the number of death claims received per day. So our time by the insurance company is the day. That's the time period. It's a day. The number of arrivals at a car wash in 1 hour, and the time is 1 hour. The events are the arriving of the cars. The number of traffic accidents per month on a busy junction. The number of traffic accidents per month. So our time is what? It's the month. And the number of second-year economics students dropping out from the program during a course of the year. So the time period is what? It's 1 year. So always here we have an element of time. We want to see the number of events that will occur between that specified period of time. Okay, what are some of the properties now? The probability of occurrence is the same for any two intervals of equal length. So this is what I'm trying to say. The probability of occurrence is basically just the same for any two intervals of equal occurrence. For example, if we say in 1 week, the probability of success is 0.5. Okay, it means even in next week, it will still be 0.5. Like it will continue like that. As long as the time period is is still the same. The occurrence or non-occurrence in any interval is independent of the occurrence or non-occurrence in any other interval. So there is issue of independence again. What we're trying to say is that the happenings in this, let's say, for example, you're dealing with the month. This month, they are not interrupted, or they're not dependent on the occurrences next month, or the occurrences next month don't depend on the occurrences this month. Yeah, so that's about Poisson distribution. So you just pay attention to the element of time. So now, the random variable X is said to have to follow the Poisson distribution if the discrete probability distribution is given by this formula, okay? Lambda, we read this as lambda, X, E function. You get the E function is always gotten from the calculator, negative lambda J, negative lambda all over X factorial. Okay, over X factorial. So now listen, who is lambda? What is lambda? Lambda is the mean. We're always given the average. That on average, take for example, the number of, let's say the number of cars that come to the car wash within 1 hour. They will tell us that on average, always, on average, we have 5 cars that come to this car wash per hour. Okay. Then the question is that what is the probability that you get 20 cars in 2 hours? Follow the nature of the question. If you are given that on average, that's your lambda, only 5 cars come per hour. If you are given 3 hours, what is the probability that you have 20 cars? So yeah, that's how you do this. What is your x? Your x is the probability of success. So the 20 cars is your x. That's the question you have. The e function is always given. It's given on your calculator. It's approximated to be 2.7180. Yeah, it's a continuous number to something. Yeah. Yeah, it's approximated to around here. So that's your e function. And your lambda will always be changing because it's a mean, and the x, that is the probability of success. That's your success. Now, observe that your formula can still be changed to this one, written or expressed as this one, not really changed, expressed as this one. Why do you express it in this way? This is just because the time is greater than 1. Once you find that the definition of time is greater than 1, okay, that you are asked is greater than 1, then you have to use this formula. But the previous one that we had, this one, when time is 1, we know that once we multiply this lambda times t times time, it will just be still lambda. So that's why you never had this version, you don't have t, because we assume that since our t is just 1, there is no need of writing it. X factorial. An example shall do well. An example will do better for this one. The average number of days an EC student will be absent from the class is 5 days in a month or per month. So it means that your average, your mean, is 5 days in a month. So your lambda is given as 5. Then your time interval is defined as a month. It's basically 1 month. That's the definition of your time. Then your x, now listen to your x. It's a probability of success. So it is given here as find the probability that a student will be absent for 4 days in a month. So your x, that's the probability of success. Whenever the student is absent from class, that's your success. So we have 4. So on average, this student doesn't go to class for 5 days per month. So the question is that what is the probability that this time around, this one will just be absent only for 4 days in a month? That's the question. So how do you go about it? Everything has been defined for us. We just need to do the replacements. Just replace into your formula. Just do the replacement in the formula. So lambda t to the power x, the power x, e function, negative lambda time all over x factorial. What's our lambda? Our lambda is the mean, which is 5. And our x, that's the probability of success given as 4. And our time is given as 1 month, so it's 1. So once you do the computations, you just replace into this formula, everything, like everything. Our lambda is 5, so it will be 5 times 1 to the power your x is 4. E function, I've already approximated, I've already given it the approximation as 2.7180. Yeah. It's 2.218. Yeah. You can confirm from the calculator. You can just confirm from your calculator. This E function is always there on your calculator. You shift E function. It's there. Given us 2 point what? None of us knows how to do the E function. 2.818 something. Yeah, but it's around here. Yeah, that's the E function. So replace the E function here to the power negative lambda. Just replace everything. And you know how to do factorial, right? When you check on your calculator, the upper left has got this button, which is just right like this, factorial. It should be upper. If it's upper, then you just do shift, then factorial. So you write 4 shift, then you press that button, it will give you factorial. 4 factorial should be able to give you the answer down here. 4 factorial simply means 4 times 3 times 2 times 1. That's the 4 factorial. Yeah. So once you get the the factorial and divide into the upper one, the upper expression, you get that as a solution. So basically that's what you just do. All right. The second question says, what is the probability that 4 and 6 days in 2 and 3 months respectively, the student will be absent for 4 and 6 days? I've already said that and means multiplication, right? And means multiplication. So this student will be absent for 4 days. What's the time? The time is 2 months. And then 6 days in what? In 3 months. Have you seen that now? What has just changed? It's the same formula. You're just replacing. What has changed is just the time. Okay, where there is 2 or t, you put these different times, and you do for this one, this x, the number of days. That's your x. The small x, this one. The small x, this one. You do for both of them and add. Once you add, oh, no, you're not adding, you're multiplying. Is and sorry, you are multiplying. Do for this one on top and for this one down, you multiply. Just multiply, you get the solution. So when the time is 2 months and the x is 4 days, when you do all the computations, you should get this as a solution. Basically, the 4 is the number of successes. So you say 4 factorial. 4 factorial. I've already said what factorial means. You can easily get it from a calculator. Just guided that on your upper left, you do shift, then you place where the perpendicular, you should get that x. There is that part where there is x, something like this.
It's
Then on top,
it's 24.
It's 24, right?
That's right.
Yeah. Yeah, so that's how you basically do it. So just do that, then you multiply these 2 solutions that you get. Should multiply the 2 answers. And once you do the multiplication of the 2 answers, these 2 answers, you should get this as the final answer. Did you get this one? All right. Then let me just comment on how you find the mean for Poisson. The mean for Poisson or expected value for Poisson is just given as lambda. Okay, so the lambda is NP. N times what? Times P. So you multiply. All right, yeah. So it's basically N times what? Times P. So N is the, you know what N is? The number of trials, and then you have P, the probability of success. You multiply the two, and then you should be fine. Okay. The geometric distribution is the easiest and the last one, probably. Not really probably, that's what is there. It's the last one. So under this one, we define it like this. The distribution is basically related to Bernoulli trials. So what do we mean by Bernoulli trials? We mean that you just make just like the binomial one, but you just make one trial, not that not that you have make many trials. That's under Bernoulli. You just make one. But what is there is now the difference is that the number of trials under geometric is not fixed. Okay. So the random variable is defined as the number of trials that are required to achieve the first success. Take for example, if you are drilling a borehole, you have those pipes, right? You don't know how many pipes that you're going to use for you to finish drilling or to succeed. So now, what is there is that under this one, the number of trials that are required, they are not fixed. Okay, it's open-ended. You can keep on doing until you do what? You succeed. That's a difference. But under binomial, it's different. We have a fixed number of times. You say, okay, what if you do it in 20 times? Okay, but for this one, it's just open-ended. Okay, if you do it again and again and again without giving up, okay, how many times can you, what's the probability that you're going to do what? To achieve this thing? Maybe when you do, or like how many times should you try for you to get the success or the first success? Yeah, it's just like this student maybe has been, God forbid, the student has been repeating the course again and again. It's open-ended. Then what is the probability that how many times should this student repeat until they pass that particular exam? It should be open-ended. The question is not oh, that's about the what's this? I kept on talking alone. The mic was off. I'm sorry. I was talking and talking
Well,
continuously.
actually, we were wondering, we thought maybe it was the network.
No, I was talking and I continued teaching. Okay. Anyways, I'm sorry for
Maybe,
that.
maybe you can just repeat for us what you were saying.
Yeah, that's what I'm going to do actually. So I was just trying to say that with the geometric probability distribution, it is almost similar to the Bernoulli trials or the what we see under binomial. But the difference is that the number of trials is not fixed under geometric. It's not fixed. We saw that under binomial distribution, we are asking that what is the probability that we're going to succeed if we try, we're going to succeed when you try maybe 5 times. What's the probability that we'll get such a success if we did this thing such a number of times? But for this one, it's more like I was giving an example of drilling, someone who is drilling a bore. You don't know how many pipes you're going to use. So we ask that, how many pipes are you going to use until you succeed in drilling that bore? Okay, so it means that it is open-ended on the number of pipes that you're going to do, okay, to use for you to achieve that thing. So once the number of trials is not fixed, then you have a geometric distribution. Even in this one, you have the probability of success, the probability of failure. Then you also have this X now. Pay attention to the way how X is defined. This is what is more important. The only difference from what we had under binomial, we had the combination part. This part is not there here. The way how the X is defined, it is defined as the number of trials before the first success. How many times should you try before the first success? That's your X. And P is always the probability of success on a single trial. Okay. An example should be able to do. An example should do. And our example goes as an oil company has determined that the probability of striking oil on any particular drilling is the probability of striking is 0.2. That's the probability of your success, which means 1 minus P, the probability of your failure should be 0.8 because it's 1 minus 0.2. The question continues. What is the probability that it would drill 4 dry well of 4 drills before striking oil on the 5th drill? On the 5th what? On the 5th drill. Okay. So how many times, what is the probability that the person will do 4? Like they would drill 4 dry wells before striking oil on the 5th drill. Like they're keeping on drilling again and again. But what is the probability that they will do 4 and then on the 5th one, they should be able to succeed? Okay. So we have already defined the elements for us. Our P is given as the probability of success in one independent trial, and it is given as the probability of striking oil on any particular drill is 0.2. Therefore, the probability of failure is 1 minus C, 0.2, which is 0.8. So now, what is our X then? What is our X? Our X is the number of trials that we have to do, okay? The number of trials that we have to do until we reach the first success. So we are told that we are reaching our success on the 5th what? On the 5th drilling. When you do the 5th one, then we are going to do what? We're going to strike. Yeah, we're going to strike on the 5th drill. So therefore, our X, the small x is what? Is 5. So in our formula, this same formula of ours, we are saying the probability of success 1 minus C, probability of success, which is C, probability of failure is X minus C, 1. Then you just compute this like 0.2 times 0.8. Our 0.8 is the probability of failure. X, our X is 5. 5 minus 1 is basically 4. 5 minus 1, it is 4. And once you compute this on your calculator, you should be able to get the probability that you drill 4 dry wells before striking oil on the 5th drilling, or on the 5th drilling. Yeah. So the probability of success is 0.0, or the probability that we are going to achieve this on the 5th drilling is 0.8192. So that's our probability. The probability is 0.08192. Okay. Any question from anyone?